everyone. Let's talk about Chapter 5, Eigenvalues and Eigenvectors, Session 5.1, Power Method. So first, let's recall the definition from linear algebra. The number lambda is an eigenvalue of the n by n matrix A, provided there exists a non-zero vector v such that AV equals lambda v. What does that mean? Okay, this is the vector v, and we know A adds on this vector. This is another vector, right? This says that A adds on or applies on the vector v. This new vector is going to be parallel to the original vector v. So we know two vectors are parallel if they're constant multiple of each other. So that's why there is lambda such that AV equals lambda v. Then in this case, the vector v is called an eigenvector of the matrix A. We also say that the eigenvector v is associated with the eigenvalue lambda, or that eigenvalue lambda corresponds to the eigenvector v. So far, so good, everybody? So the eigenvector is the vector that the matrix add on it, and it won't change the direction of the vector. Okay, we mark. If the eigenvector is 0, then the equation A times 0 equals 0 holds for every scalar lambda and has no significance. This is why only non-zero vectors qualify as eigenvector in the definition. Okay? So we need non-zero vector to be the eigenvector. Okay. Next, let lambda and v be an eigenvalue and an associated eigenvector of the matrix. If k is any non-zero scalar and let u be k times v, then AU equals A times k v. And because k is just a scalar, we can the multiplication of scalar is commutative and associative, right? So we can move the k right here. Then because v is an eigenvector, okay, because v is an eigenvector, then AV equals lambda v. Now, because lambda and k, they're just multiplication of scalar, is associative and commutative. So we can move the lambda in front. Now we get lambda u. Okay, so now we have shown that AU equals lambda u. So then we can get u. This u is also an eigenvector. Okay, associated with the eigenvalue lambda. So far, so good, everybody? Okay, questions. Given the matrix A, how can we find the eigenvector? So we call that AV equals lambda v, but we can consider lambda v as lambda times the identity matrix. Okay, so this I is the identity matrix. We have 1 on the diagonal, and then the rest just zeros. Okay? So now we can move the right hand side to the left. We get AV minus lambda IV. Okay, now we can factor out the v. Remember, this is matrix vector multiplication. It's not commutative. Okay, so v is on the right, then it has to be stay on the right. So we have A minus lambda IV equals 0. For fixed lambda, this is a homogeneous linear system of n equations in the n components of v. This system has a non-trivial solution v is not 0, if and only if the determinant is 0. So far, so good, everybody? Yeah, this is a homogeneous linear system, and from linear algebra, we know that the homogeneous system could have the solutions can only have two possibilities. We have a trivial solution and also a unique solution that is the trivial solution, the zero vector, and we can have infinite many solutions. Okay, so these two possibilities, and here, if the determinant is not 0, then we get a unique solution, which is a trivial solution, 0. If the determinant is 0, then we have infinite many solution. Then we can find an eigenvector, a non-zero eigenvector for it. Okay, so the determinant equal to 0. This equation is called the characteristic equation. And with theorem, the number lambda is an eigenvalue of the n by n matrix A if and only if lambda satisfies the characteristic equation. So the determinant of A minus lambda I equals 0. Okay, this is a kind of review. We talked about this before in linear algebra. So algorithm to find the eigenvalues and eigenvectors. First, solve the characteristic equation A minus lambda I, the determinant equal to 0 to find lambda. Then for each eigenvalue lambda, we solve this linear system A minus lambda I times V equals the 0 vector to find the eigenvectors associated with lambda. And in general, for 2 by 2 matrix A minus lambda I means we just subtract lambda on the diagonal elements, and then the rest, the other entries stay the same. And then what's the determinant? We just cross multiply, but we subtract. So that's why we have A11 minus lambda times A22 minus lambda minus A21 times A12. Okay. And when we solve for lambda, why do I miss the lambda here? Let me copy it down right here. When we solve for lambda, we get 3 possibilities, right? This is a quadratic equations. So we can use quadratic formulas, and well, we can have 3 cases. We can have 2 real roots, we can have 1 repeated root, or we can have 2 complex conjugate roots. So far, so good. Okay, let's do one example here. So if you totally forget what eigenvalues, eigenvector, please, you can go to my course website, go to my linear algebra and differential equation course, and then find the notes and videos in chapter 6. Okay? Let's see. Let's find eigenvalues and eigenvectors for the following matrix. We call it A. First, what we do is compute the determinant of A minus lambda I. And what is that? Well, we subtract lambda from the diagonal elements, and the other entries stay the same. And because it's 2 by 2 matrix, we just cross multiply, but we subtract. Right, 5 minus lambda times minus 4 minus lambda. Subtract minus 2 times 7. Well, let's see. 5 times minus 4 is minus 20. 5 times minus lambda is minus 5 lambda. Minus lambda times negative 4 is plus 4 lambda. Minus lambda times minus lambda is plus lambda squared. Minus become plus. 2 times 7 is 14. Is that okay, everybody? And let's reorder it. So we have lambda squared. How many lambda? Minus 5 lambda plus 4 lambda is minus lambda. And minus 20 plus 14 is minus 6. So we set this guy equals 0. How do we solve it? Well, this is quadratic equation, but if sometimes we can factor it, then that's good. If we're not able to factor it, we can always use the quadratic formula. Okay, how do we get minus 1? Minus 3 and plus 2 will give us minus 1. Then lambda equals 3 or lambda equals minus 2. So these are the eigenvalues. So far, so good, everybody. And then for each eigenvalues, let's say lambda equals 3, we want to solve the system A minus lambda I times V equals 0. Let V be xy. Now, this is the same as to solve the arithmetic coefficient matrix A minus lambda I, but lambda is 3. So you plug in here. 5 minus 3 is 2. and we have 7. -2 minus 4 minus 3 is -7, and then this augmented coefficient matrix, the right hand side is the 0 vector, so that's why the third column is just zeros. And you can see, well, when we add R1 to R2, then my R2 just consists zeros, and this is always the case, right? Because eigenvector, here, this is a homogeneous linear system. In order to have a not unit solution, infinite solution, we need to have a row consist entirely of the zeros. Now, this is x, this is the y, this is the right hand side. This guy tells us that 2x plus 7y equals 0. Right, and what is x? Well, we move the 7y on the right, and then it becomes minus 7y, and then we can divide it by 2. Right? So we can pick, okay, let me write down this first. So v equals, x is minus 7 over 2y, and y is y. We have the one free variable, right? So, and then we can pick y to be, in order to get an integer for the v, we can pick y to be 2. Then the v is minus 7 and 2. So this is the eigenvector associated with the eigenvalue 3. So far, so good, everybody? Okay, let's continue. Lambda equals minus 2. And then we do the same thing for the augmented coefficient matrix. 5 minus -2 becomes 7. -4 minus -2 is the same as -4 plus 2. It becomes minus 2. Well, you can see, well, I can factor out, we can divide it by 7 for the first row. And then you can see now the first row, the second row is the constant multiple of the first row, right? So here I'm combining 2 steps into 1 steps. So we can then use 2R1 add to R2 to kill the R2. And this is x, this is y, this is the right hand side. And then the first row tells us that x plus y equals 0. Then what is x? Well, minus y, right? So v equals x is minus y, y is y. So then we can pick y to be, actually, you can pick y be any non-zero number, right? We can pick y to be 1. Then v is minus 1 and 1. So this is the eigenvector associated with the eigenvalue minus 2. Okay? So, so in this case, you see, when we have 2 real roots, this is the case, our example is just the case with 2 real roots. Then each real roots, so we have 2 real roots, each real root has 1 eigenvector. Okay? If we have 1 repeated root, we might have 2 eigenvectors. Or we might have only 1 eigenvector. Okay? If we have 2 complex conjugate roots, then each complex root will have, so has 1 eigenvector. And those roots, those 2 complex roots are complex conjugates. And each complex root has an eigenvector. So those 2 eigenvectors are actually complex conjugates. So far, so good, everybody. And if you want to see example of these, go to my MA 2100 Linear Algebra and Differential Equation, Chapter 6 notes. Okay, everybody? So in there, I have examples of all 3 cases, And I also give you examples for a 3 by 3 matrix instead of just a 2 by 2 matrix. Alright, let's continue. Okay, so how to use MATLAB? To find eigenvalues and eigenvectors for the following matrix, to find the eigenvalue, we use MATLAB's built-in function. So we use EIG. This is like eigen of A. Okay, EIG of A. So it returns a column vector containing the eigenvalues of the square matrix. Okay, so this is what you see after so we insert this matrix in MATLAB, and we input the syntax E equals EIG of A. Then we will get 3 numbers. So this is a 3 by 3 matrix, right? So we have, in this case, we have 3 eigenvalues. Okay, so we have 3 eigenvalues. Okay. It is also possible that we can have like only 1 eigenvalues, but multiplicity is 3. That's also possible. Okay. Next. Then, to find the eigenvector associated with each eigenvalue, we can put VD equals EIG of A. So it returns a diagonal matrix D of eigenvalues, and the matrix V whose columns are the corresponding right eigenvectors. So that's A times V equals V times A. Okay, so this is what happened after you insert VD. Okay, you get V. So this is the eigenvector associated with this eigenvalue, and this vector associated with this eigenvalue, and this vector associated with this eigenvalue. So far, so good, everybody.